We turn our attention now to flow in porous media, and we're going to be talking about saturated flow in the subsurface, or groundwater flow. And we're going to start by studying one of the foundational observations and the most important laws in all of hydrology, something known as Darcy's law. So way back in 1856, in Dijon, France, a hydraulic engineer working for the city named Henry Darcy published a set of results. And Darcy had spent his career trying to understand how to come up with clean drinking water for the city, specifically by moving the water that people drank through sand filtration systems. And Darcy had done a number of experiments and had observed something really important about the way that water flows through sand in the subsurface. So one of Darcy's experiments was in the lab, and it consisted basically of some lab bench here and a big tube, a cylindrical tube, and there was water that could flow into the tube through some hose and water that could flow out of the tube through some hose. And this water flowing in and out is the same. You let it get to steady state. And it's flowing at a rate Q, volume per time. There's some other things that we can describe about this particular tube. It had some cross-sectional area A. It had some length, delta L. And there was another feature that was pretty neat, and that was that there were these little smaller tubes that were kind of plugged into the side of the big tube. And these smaller tubes were open to the atmosphere on the top, but connected to the inside of the tube on this end. And these allowed kind of a measurement of the level of the water, or the pressure inside of here. So this is what this is depicting, water inside here. So Darcy did this experiment and made the following observations. 1, the flow rate through here was proportional to the cross-sectional area. So a bigger tube, you got more flow rate, all else equal. 2, the flow rate was inversely proportional to the length of the tube. So if you have a longer tube, all else equal, you're going to get a slower flow rate. Finally, one of the other key observations was that the flow rate was proportional as well to the difference in height of these two tubes, which we'll call delta H here. And if we were to call this one here H2, and this one here H1, delta H would equal H2 minus H1. So the magnitude of this difference. If there was a bigger difference between these, there would be greater flow through the tube. And so changing the parameters of the system, these kinds of observations always held. Changing these three variables resulted in linear increases or decreases in the flow rate. And so Darcy put this all together into a law, which is Darcy's law for saturated flow or groundwater flow. And it's the following. Q is equal to negative K delta H over delta L. This K term, this is a constant of proportionality. Remember, these are just proportional to. This is what makes this an equation. And K here is this constant known as hydraulic conductivity. And as we will discuss in great detail later, it's related to whatever is in here. So this is maybe a sand pack, for example. The other thing that there's another way that Darcy's law is commonly written, and you should be aware of it. It's written with a little q. Whoops, I'm missing one thing here, A. We also said that it was proportional to A. It's written with a little q, negative K delta H over delta L. And this little q here is known as the specific discharge. This is the overall discharge. And this little q here is big Q divided by A. And so if we were to check the dimensions on this, we know that this is a length, this is a length, these two cancel out. This is a length cubed per time divided by a length squared. This must have dimensions of length per time. And since these two cancel out, these also must be the dimensions of this hydraulic conductivity term here, K.